All right, folks, today we're going to go ahead and talk about what is biomechanics. Really, what biomechanics comes down to is it's going to be the combination of both life and then the mechanics, meaning we're talking about physics. So when we're really looking at just what's going on with mechanical movement in living organisms. And that's going to be divided into four basic sub-branches. We've got statics, and that's going to be something that's in constant motion. Now, rest is a constant state of motion. When you're riding a bike, your legs in theory should be in a constant motion. Dynamics is going to be acceleration. Acceleration is change in velocity. So this would be a car at a dead stop accelerating to its top speed. Or you're sitting in the car and then you put the brakes on so you slow yourself down. Anytime we're changing the speed an object is going. Kinematics is going to be the appearance or description of what's going on in the motion. And then kinetics is all about force we're producing. So for those of us, picking up an object, setting it down, and how much force can be required to lift a barbell, to lift yourself, to move a heavy object. So further examples of kinematics, like we said before, it's going to be that constant motion. And now we're talking about sequencing of those motions, the size of the areas that are moving, and how we're going to time up this movement. So a great example of this would be something like swimming. If you've got bad sequencing, timing, and your movement patterns are not efficient, you're going to waste a lot of energy. You're not going to go as fast. Kinematics is going to be looking at those forces, both internal and external. So when an athlete is swinging a baseball bat, yes, they have to produce force to move the bat, but they have to produce force to move their arms, to move their shoulders, to move their hips, to move their entire body. And each of those segments of the body are going to require force to move them, to accelerate them, to get them to the velocity we're needing. Now, kinesiology is a big umbrella, and underneath it, we have biomechanics, we have adaptive physical education, we've got motor behavior, motor learning, we've got a wide variety of aspects of just looking at what's going on with human movement. And this also plays into sports medicine, where biomechanics plays a big key. Physics is a harsh mistress. Any of you guys that have played a sport and had a very large human fall on you, you know it hurts. Or you've ever collided with a solid object at high speeds. It hurts. We're going to talk about friction, which is two objects sliding on each other. And if you guys ever slid across concrete or some other very rough and very solid surface, you're going to donate skin and be in a lot of pain. So biomechanists are going to be able to study a lot of interesting questions, one of which is when we're no longer exposed to gravity or go through periods of detraining, how much muscle mass we're going to lose, how much bone mass we're going to move. When eventually, hopefully, humans are living on the moon and living on Mars, it turns out, well, they're going to spend a solid amount of time traveling specifically to Mars with no gravity. And then when they do get to the moon or do get to Mars, they're going to be exposed to much lower amounts of gravity. And these lower amounts of gravity are going to cause us to atrophy, to lose muscle mass. And if we've really done nothing for the past 6 months to a year to traveling to Mars, and then all of a sudden we have to be highly physically active, we're going to have a hard time because we're going to be too deconditioned. We're also going to look at things like the effects of different pieces of equipment we can use when we're doing things like training. Like what's going to occur when we use a belt when we're lifting weights, when we're using knee sleeves, elbow sleeves, wrist wraps. How is that going to enhance our performance? And at the same time of how are we doing things when we're learning, when we're developing, when our body is changing? Due to the size of your head relative to the rest of your body when you're a baby, if you really wanted to mimic what it's like to be a baby, you would have to wear a football helmet with a 45-pound weight plate attached to it to have the same amount of mass distributed that high in your body, which lets you know that's why kids always have such good posture and they've got such great squatting technique. Because if they don't, they're going to fall apart and risk injuring themselves. So we unfortunately are not meeting in class, so these are not going to be relevant as they would be in the past, but the idea is that you guys still have a conversation with the people that you're around and look into, are you understanding? While you're going through these slides, stop, pause, write down questions you have, write down issues you have. Feel free to email me those questions. I'd be more than happy to go into further length. Either I can shoot a little video and put up some more slides on it, or we can go ahead and just have a conversation. Just take care of it by email or even a phone call. Gait Research is looking at how we're going to move. Obviously, individuals, there's sometimes neurological issues, there's sometimes physiological issues. Obviously, individuals that unfortunately have a stroke are going to have to relearn how to walk. And so making sure that we have ways to help make them be successful and not risk injuring themselves any more thoroughly. So there's a number of things that biomechanics are going to help us study. We're going to be able to look at simple things like, does stretching really enhance performance? Does it help decrease injury risk? And it turns out No, it doesn't help with performance. It might decrease injury risk, and it's more important to do it at the end of a training session. Then we can look at things like typical injury patterns in sports. Like, turns out there's a major elbow surgery named after a very successful baseball pitcher, because that's part of the elbow that takes a lot of beating from doing a lot of throwing. And then what can we do to make ourselves more efficient as a sprinter, as a thrower, as a lifter, as insert any sport athlete? What's the most efficient technique we can use for a given individual? And what's the most efficient technique in general that we can employ when working with athletes? So we can see how there's been progressions in equipment, anything from literally athletes wearing that moisture wicking fabric so they're not going to be literally weighed down by a sweaty of clothes, to things like enhancing different safety equipment, like the improvements that they're trying to make to the NFL helmets to decrease concussion risk, along with what can we do to still allow individuals to move and be healthy. Like, linemen wearing knee braces decrease the risk of injuring their knee, tearing an ACL, but at the same time still allow them to move and be athletic on the field. So we're going to use biomechanics for a variety of reasons to go ahead and study different components of success. And we're back. So we're going to use biomechanics to simply really use science, use physics to help us figure out what can we do to help make people more efficient with their technique, to make sure that we're using equipment to optimize performance for whatever that athlete's role is, to really assess, are our training methods that effective, and what are things that we should do in order to enhance the performance. So what should we do in the weight room, what should we do in the field, what should we do to make sure that we decrease the risk of injury, and also to understand how the body changes with time and how different parts of the body are more likely to be injured at different points in age. Because it turns out when we're going through our growth spurt, we actually have the greatest risk of injury for a lot of the soft tissues, because they're having to increase in length so rapidly that you can really injure an athlete if you don't know what you're doing. So it's important that we use science. And all we're doing is attributing values to things we've already been able to observe, of really seeing, okay, this is what's occurring whenever person A is doing this. Like, how much force do you really have to get and transmit through your foot, through your ankle, through your knee, through your hip when you're jumping in the air? And what happens if we absorb those force inappropriately? Do we increase our risk of injury? So a component to understand is what's known as anthropometric factors. This is going to be the size, shape, and weight of different segments of the body. If we know how long your arms are, how long your legs are, how much each part, so how much does your hand weigh, how much does your forearm weigh, how much does your upper arm weigh, when you're throwing a ball, we're going to figure out how much force, and when it's rotational force is referred to as torque, we're going to have to produce in order to get that hand to accelerate with the ball in it, to get that forearm to rotate, to get that upper arm to come through, and then obviously the rest of the body and so on. It's just a math problem. It's a complicated math problem, but it's a math problem, and we're going to be able to approach it and use science to help us. And specifically, what we're going to be doing is mostly quantifying variables. Now, quantifying is when we actually give a true number to a variable, whereas qualitative variables are giving it a quality. So this is where we're going to talk about someone is tall, short, fast, etc. But like, they're tall. What's tall mean? Well, are they tall in that they're 7 feet, which I think everyone would agree, or are they tall in that they're 5'5" and it's a 4 foot tall person saying that that person's tall? Because relative to them, yeah, they actually are tall. So we're going to try to quantify variables when we can. And if you have questions over what that means, please let me know. In fact, here's a great example of the difference between a quantitative performance and a qualitative performance. It's not a great joke. Whereas when we look at athletes, typically we're going to be giving them qualitative assessments and giving them qualitative feedback. If your coach told you that you need to go ahead and produce 80 more newtons of force with your left leg in order to be successful at that event, you're going to probably give them a funny look. But instead, if the coach said push harder off your left leg, you'd be like, okay, I can do that. So even though we utilize qualitative, we still need to have a respect and understanding for the quantitative, because that's really showing us what's going wrong with our system. And are we inappropriately applying that force, or do we not have enough force to apply in the first place? So another point to pause, reflect, and think about how you can further understand this information. Thank you guys for listening. Have a great day. Whatever questions, comments, concerns you have, please let me know.